So before we start this set of lectures, we need to remind ourselves about the common ion effect. So the common ion effect, that dealt with solubility, and it said that if we have a certain solid that's dissolved, if we add a similar ion or a common ion, it will shift the equilibrium back towards the solid side. It's just a form of Le Chatelier's principle. So the same thing would happen with weak acids and weak bases. They do set up an equilibrium, so hydrofluoric acid sets up an equilibrium between hydronium and fluoride ions. If we add some Kf, which is a solid, so that's going to ionize completely into K plus and F minus. So this is a soluble group 1 metal, so we know it's 100% dissociation. Then we're going to have that common ion right there, so the two F minuses. The addition of extra F minus is going to cause this equilibrium to shift back towards HF. It's not going to make any change in this reaction because it's 100% dissociation, no equilibrium. But this one right here, it's going to cause to go back that way, and if it does that, that's also going to decrease the concentration of the H3O+. If you decrease the concentration of the hydronium, you're raising the pH up more towards neutral. We could do the same thing with a weak base. It sets up equilibrium. If we add something to this system right here, like NH4Cl, the NH4, the ammonium, is going to drive equilibrium back towards the left, thus decreasing the OH minus concentration, thus dropping the pH. And we use the common ion effect to create what's called buffers. Now, I know what you're thinking about when you hear the word buffers. You're thinking of me. But we're not talking about that kind of buff. We're talking about an acid-base buff. The buffer we're talking about is one that resists changes in pH. So when small quantities of strong acid or strong base are added to a buffered solution, the changes in pH are very, very small. Normally, a small amount of acid added to a solution is going to drop the pH, and a small amount of a strong base would raise it dramatically. But in the case of a buffer, very, very tiny, tiny changes. What they're composed of are these two recipes right here. So it can be a weak acid and its salt, that means extra conjugate base, or a weak base and its extra conjugate acid. So here's an example of a buffered solution. We have acetic acid, which is a weak acid, and then we dissolve in it sodium acetate. Sodium acetate, 100% dissociation, which means it produces lots of both sodium and acetates. And this acetate right here would be the conjugate base of this weak acid. And so what we have then is we have a weak acid and extra conjugate base. In this solution alone, there is going to be a small amount of acetate, but what makes it a buffered solution is the addition of extra conjugate base. So that makes this a buffered solution. Why is it that this resists change in pH? Well, remember, what changes pH is the addition of either H pluses or OH minuses. So if we add H pluses to this solution, okay, we add extra H pluses, well, those extra H pluses can go ahead and bond with this guy right here, which is going to then eliminate that H+. Remember, the conjugate base of a weak acid, which is what acetate is a strong base. That means it's a very, very powerful proton acceptor. So if you put more protons in this solution, it's going to accept those and drive it back to CH3COOH, which has no pH itself. And so it's going to absorb those protons. By absorbing them, it's going to resist a change in the pH. If we add hydroxides to this solution, they will join with the H pluses to make water, which is neutral. And then what happens is, since we have pulled that out, Le Chatelier says that it's going to shift back up to fill that void, and so then the CH3COOH is going to generate another H plus here and another acetate there. And so overall the pH won't change because the H plus that we're putting in is just replacing the one that was there before. So the ability of a buffered solution to absorb those protons or hydroxides is called its buffering capacity. And so the higher the concentrations of the HA, so that would be the weak acid, and the A minus, that would be the conjugate base, would determine what its buffering capacity is. So the more, the better. The best conjugate, or the best buffers, though, have equal concentrations of HA and A minus. So an equal concentration of weak acid and its conjugate. So when buffered solutions are created for practical application, they're designed to resist change in pH. So if a pharmaceutical company or any kind of lab wants to maintain a system where pH stays the same, so it doesn't change, they would want to create a buffer. And if they pick that pH, they need to figure out what they need to add. So what acid and what conjugate will they need to use? And so to do that, they use the Henderson Hasselbalch equation. And so the equation is pH is equal to pKa, and that would be the Ka of the weak acid in this case, plus the log of the conjugate base concentration divided by the weak acid concentration. So typically to get the conjugate base, we add a salt, and so that would be the concentration of the salt. The weak acid would be the concentration, the molarity of that weak acid. So when we're trying to pick a pH of a certain sort, we would usually pick one that has a pKa close to the pH that we want. So if we want a buffered system at, let's say, a pH of 8, we would find something that has a pKa close to 8, because then we could get concentration of our A minus and HA to be equal, which would be 1. That creates a log of 0, which means pH equals pKa. So the weaker the acid, the higher the pH of its buffers that we could create with it. Slightly stronger weak acids would have lower pH values. So here's an example. Let's say we want to create half a liter of a buffered solution that's buffered at about 4.80. And we want to have similar concentrations of HA and A minus, which means that we want to get one that has a pKa pretty close to 4.80. So down here on this little chart, there's actually a typo, 3.18. That would be the pKa of C9H8O4. The Ka value for that acid is actually supposed to be 6.6 times 10 to the negative fourth. And so the negative log of the Ka, that would be pKa, for this acid is 3.18. The other acid, which is acetic acid, has a Ka of 1.8 times 10 to the negative fifth. So the negative log of that right there would be 4.74. And so then the logical choice here would be the acetic acid to prepare a buffer solution. So that means we're going to need acetic acid and its conjugate base, which would be some form of acetate. And then it wants us to estimate the ratio that would produce that, and so we're going to use the Henderson-Hasselbalch equation for that. So the Henderson-Hasselbalch equation for this one, the pH would equal pKa plus the log of the acetate divided by the acetic acid concentrations. And in this case, it wants us to find the ratio, and so what we're going to be solving for then is this guy right here. Okay, so the ratio would be of acetate to acetic acid. Okay, so we want a pH of 4.8. We found the pKa was 4.74, and so then we can just solve for this ratio right here. That's going to be taking the inverse log of 4.8 minus 4.74. And so the ratio of acetate to acetic acid that we want to achieve is about 1.1, and that'll give us a pH of 4.80. So it's close to 1, close to the same concentrations. Henderson-Hasselbalch equation is actually handy for weak acids and bases, even if they're not a buffered solution. So you can use it to compare the pH to the pKa, and that's going to tell you about the ratio of the dissociated acid to the undissociated acid. So basically how much conjugate and how much undissociated acid there is. So anytime the pH is less than the pKa, that means the acid form is in the higher concentration. So the number on the bottom, that would be the HA, is in the higher concentration. If the pH is greater than the pKa, that means the base form, or the A minus, would be in higher concentration.